Okay. All right, we've been talking about moving these particles from high to low concentrations, moving them with and against their concentration gradients, passive active transport kind of stuff. When the sodium, for example, if you go back to here, you're moving, notice you're moving sodium and potassium ions on either side of the plasma membrane, whether it's, you're moving potassium to the ECF, you're moving sodium to the ICF, or the intracellular fluid. When you do this, what you start doing is loading up on one side compared to the other, and you start to create situations where there may be more sodium on one side, in this case the outside, and more potassium on the inside, for example. And when you do this, you create a situation that allows movement to occur under certain circumstances of these ions. They can come flooding in, or they can go flying out of the cell if channels become open, allowing them to move according to their diffusion gradient. So one of the things that I want you to point out here is the word potential here. It says all cells establish a membrane potential, and what I'm talking about here is whenever that sodium and that potassium moves, something else to consider is not just the fact that they are moving and the fact that they are little atoms or ions that are moving around, but they have a charge with them as well. So we're going to start incorporating some electricity here. As sodiums are positively charged, potassiums are positively charged, these ions that form, and when they start to move to one side of the cell or the other and create an area of higher concentration, one of the things we also have to consider is the charge. Is there a greater charge potential? Is it more, for example, is it more positive on one side than it is another side? And that's something else that will flow according to a gradient, is electrical charge. It'll flow from a place, for example, where there's more positives to a place where there's more negatives. So that's what I mean here. There's a separation of charges across the plasma membrane. And the reason of this is because it's dependent upon, obviously, the concentration of the sodium, the concentration of the potassium, the concentration of the chloride, and that kind of stuff. And on top of that is, all this is happening at one time. The sodium-potassium pump is moving things where they need to go, but also things are just leaking through the plasma membrane. Some channels are open, allow sodium to leak through. Some channels are open for potassium that allow them to leak through. And when all this is superimposed and considered all at the same time, there is a resulting potential that sort of establishes itself that seems to carry through this cell and seems to be the baseline from which it operates in terms of electrical charge. And I'll show you what I mean here. And notice this last part down here. It says a cell develops a resting membrane potential when it is not sending electrical signals. You'll see that when in Chapter 4 we talk about neuronal physiology, electrical signal is going to result from, like you've learned about nerve cells and that kind of thing. When that action potential and that electrical signal gets sent, what it actually is a movement of ions across that membrane. And when charge is associated with these positives, especially, but positive or negative charges, when they start to move, anytime you have a charge that is moving from one place to another, that's an electrical conduction. That's electrical signal. So this membrane potential that we're talking about here is sort of like a trigger on a gun that's cocked and ready to go. That's its resting membrane potential. That's its state currently, how its charges are separated across this membrane. And then once it gets triggered, it will send a signal by all of a sudden now moving according to those gradients that you've just set up. Okay, take this for example. Instead of just looking at particles, if you counted the number of particles, like ignore the plus and the minus sign for a second and just look at what we have, you'll see that there are 20 particles on either side of this membrane, assuming this is your membrane right here. Okay, there's 20 particles on this side, and there's the same over here on this side. Okay, this can't draw very well with this, so sorry. Another way to look at this, though, instead of just the number of particles, because according to the number of particles, we don't have a diffusion gradient here. We don't have a place where there's higher, the place where there's lower, where like this side would want to go to this side, or this side would want to go to this side. Okay, we don't have that situation. Nor do we have it in terms of charge. Look at the charges. Let's look at positive signs. Okay, a positive charge. Notice that there's 10 on this side, okay, and there's 10 on this side. Likewise, there's 10 negatives on this side and 10 negatives on this side. So we don't have any sort of direction that they want to flow in. Now, if you take a look at what's going on here, this is a little bit different situation. Yes, there is a particle number difference. And yes, in general, whatever all this stuff was would want to move in this direction because it would want to move to a lower concentration. But look specifically at, I guess more closely at what our true difference is here. There's a total of 25 particles over here, right? There's a total of 15 over here. So there's our total gradient. But look electrically at what's happening. Notice that you have 10 negative charges over here, 10 negative charges over here. Notice that electrically speaking, there is no, in terms of the negative signs, no electrical gradient where these electrical particles want to flow to. However, if you look at compare our positives, you'll find that there are actually more positives over here than there are over here. So you do have a membrane potential. You have a difference in electrical charges on either side of the membrane, not just number of things there, number of atoms, number of sodiums or whatever, but an actual number of charge difference. And that will drive electrical movement. You'll see that this positive charge will want to move from this side to this side. Okay, a couple things to point out here. When that happens, realize that positives and negatives tend to cancel the effects of each other out. So what we would actually say in this case is if you had to compare these two cells, not cells, but these two situations with one another, we would actually classify this as a negative side and this side as a positive side. Now, realize that this is not more negative. This right side over here is not more negative than this left side over here. There's the same number of negative particles. However, because there is a difference in the number of positive particles, we use positive and negative as a relative term, sort of in the sciences. It sort of just compares two things. This one is more positive. The left side is more positive than the right side. So we give it the connotation of positive compared to what it is you're comparing to, this right side. So that means even though in terms of the actual negative signs that are present, this right side has the same number of negatives, but since it has far fewer positives, we say that it is more negative by virtue of the fact that it is less positive than this side over here. So we give this a positive value, we give this a negative value. And what you will see then is movement from the positive, more positive side over to the more negative side, like you see in this case. And what you end up with at a cellular level is sort of a positioning of charges. You've got the way it all ends up, you sort of got everything balanced out here. You got your ECF out here with all kinds of different ions that can, all kinds of different stuff out here that can contribute to positivity and negativity. But right here, you actually get a separation of charges along the plasma membrane. A lot of these negative signs come from like proteins and organic molecules that are inside the cell that have a negative charge with them, but they're too big to be able to leave very freely out through the cell, so they sort of build up. So they tend to be, you have a lot of sodium getting cranked out of the cell, as you'll see here in a second. I'll show you again, but because of the sodium you got being cranked out, you actually get a little more positive area on the outside of the cell. And then, of course, electrically, we know positives and negatives, opposites attract, right? These extra negatives that you would have in here because of the fact that some of the sodium is moving out, and also the fact that some of these larger proteins and organic molecules that have a negative charge tend to gravitate over here towards this positive charge, even though they can't actually get across this membrane. So you get this separation of charges like you see here, this whole positive-negative rim going around the outside of the cell. Now, as far as the sodium-potassium pump goes, we've got to remember that its job is to sort of move sodium outside of the cell, right, and move potassium back inside the cell. I talked about how it's sort of like shoving it into the closet, right? You're trying to go against the natural gradient. You intentionally, what you actually do cellularly is intentionally shove sodium to the outside of the cell, and you intentionally try to pull in potassium from the cell. And we're establishing this. We do this on purpose to establish this membrane potential to sort of cock the trigger on the gun, so that when we learn about neuronal physiology, that trigger gets pulled, and then because there's so much sodium out here, it can come rushing in very quickly, and because there's so much potassium out here, it can come rushing out very quickly, and that is what's going to create that action potential, for example, when we get to nerve cells. Okay. One thing to note about the sodium-potassium pump, notice here it says it transports more sodium ions to the ECF than potassium ions. Now, some of the things we're going to talk about here is why you get this separation of charges, why there tends to be a higher positive charge on the outside of the cell, and the inside of the cell ends up being more negative. So the sodium-potassium pump, even though it's moving both sodium and potassium, what you'll find is every time it picks up sodium, it actually picks up 3 sodiums compared to 2 potassium ions. So it moves, now imagine this, it moves 3 sodiums this way. Okay, so you start building up your positive charge out here, and it only pulls in 2 positives, which are 2 potassiums, to the inside in terms of charge. So 3 versus 2. Notice that if this continues to happen, you're always going to have a 3-to-2 ratio of sodium to potassium. So what you do by moving the sodiums in 3-to-2 compared to potassium is you start building up a positive charge out here, more positives in the ECF compared to the number of positives in the ICF. So you're setting up this electrical gradient. Like I talked about before, back on this slide here, realize that you're not changing the number of negatives necessarily, you're changing the number of positives. And by changing the number of positives and giving one much more positive than the other, you create this type of situation like we have down here at the bottom. Whichever one has more positives gets to be the positive one. Whichever one has fewer positives gets to be what's called the negative one. So that's what you're setting up here. Okay. All right, so you've got more sodium out here. That means more positive charge than compared to the inside. Now notice the second point here. A resting membrane is more permeable to potassium. What that means is it's a lot, because you're loading up potassium on the inside, right? This is its highest concentration gradient on the inside. So naturally it wants to move just by diffusion from inside to outside the cell. And the thing is about the plasma membrane is that it's leakier, if that's a word, it's leakier to potassium than it is sodium. So whenever sodium's trying to move in this direction, right, from outside to inside, when it's trying to move in, it gets more resistance. It's harder for it to cross. There's not as many open channels that are chemically match to sodium. However, there are more open channels that match to potassium going this way, so it leaks out faster. So that's going to contribute to a buildup of more positive out here too. So imagine all that happening. Not only does it move more sodium out here and keeps fewer potassiums in here in terms of charge, so you get a buildup of positive charge out here, less positive charge here, you also have more of this positive charge that was in here leaking out and going back over to here because it's leakier through here and it allows potassium to move according to its gradient. Okay, so what all this means is that when a cell is resting, in other words, not conducting any sort of electrical signal, you have this potential set up where it's more positive on the outside than it is on the inside. Okay? Now, realize that there is some sodium that can leak in at the same time, but not nearly as much sodium that will normally, just under normal circumstances, leak in compared to the amount of potassium that will leak out. Okay? One thing I want to note about this slide is notice this chloride ion. Sodium and chloride tend to stick together in the body and in terms of their movement. Generally, if sodium goes in this direction, which is the way it wants to go, if it's open and allowed to, remember it's built up out here, it wants to diffuse towards the cell. And if it is allowed to, what you'll find is that chloride sort of hitches a ride and goes with it because it follows it and tags along. Think of it like that anyways. It sort of follows it and tags along because it's attracted to it, right? This is positive, this is negative. They form a pair here. And where that one goes, this one sort of follows. Now realize what that means. For any sodium that happens to be leaking in, if chloride comes in, realize it's negatively charged, right? So that can contribute to the negative side of things in here and allowing this to become even more positive outside. So the point of this is for you to see that just through normal diffusion and ionic movement, we establish these potentials. We establish this area where there's more of a positive charge on the outside of the cell than there is the inside of the cell. Okay, and that's very important. because if you measure it in science, one way to measure electrical potential, and you're familiar with this, is volts, right? You have 12-volt batteries, 9-volt batteries. What that volt represents is the degree of difference in terms of the electrical potential in where this electricity is versus where it's flowing. For example, you grab onto a 9-volt battery, it's not going to shock you very much because 9 volts is a pretty low potential difference. It's not as much of a massive movement from one place to another, but if you grab onto 2,000 volts electrical, go to a substation or something like that where it's got like this ridiculous amount of voltage, and you grab onto some of the metal there or the generators there or whatever, realize that 2,000 volts means there's a huge difference, or 200,000 or whatever. There's a huge difference between the amount of electrical stored energy in what it is you are grabbing versus what's probably going to be in your body. So because of that huge difference, it's like this huge diffusion gradient. It's like a waterfall. The second that it's allowed to diffuse, you make contact with it and give it a bridge, give it electrical conductive medium, it's going to flow through that, and it's going to flow through very quickly and very violently, and it's going to cause more damage as compared to if there was a lower voltage. Now, as far as resting membrane potential, millivolts are 1/1000th of a volt. Okay, so 1 millivolt is 1/1000th of a volt. So this is pretty small. We all have electricity flowing through us all the time because of the movement of these ions that we've been talking about. So when it all averages out and you consider all this potassium movement and all this sodium movement, what you get is an average resting potential of negative 70 millivolts, meaning the negative is in reference to the fact that we're considering the inside of the cell. That negative means the inside of the cell is more negative than the outside of the cell, to the degree of a unit we call negative 70 millivolts. Okay, that number is a very important number. You'll have to know that. So, and here's just a picture of what's happening here. As we've got sodium, like I said, passively without energy, according to just normal open channels, allowing to sort of eke in. Potassium allowing to sort of eke out, but at a greater rate. It's easier for potassium to leave for chemical reasons, according to the membrane, just under normal circumstances. And that's why we get this buildup, right, of positive charges out here versus in here. This tends to remain more negative compared to what's out here. Now, all the while this is happening so that things don't get chaotic and out of control, to try to maintain as much as we can. That's why we rely on our sodium-potassium pump to sort of keep this sodium concentration gradient loaded out here, keep forcing sodium to the outside so that things like this can happen. Okay, it can passively flow in, and to keep potassium cranked up on the inside so that this flow continues unhindered and can continue to behave under natural circumstances. Okay, and finally, all the stuff we just talked about is going to become very important when we look at nerve cells and muscle cells, because they take this membrane potential and they use it in a very specialized way to conduct action potentials, which will be nerve impulses ultimately, muscle contractions, all that kind of stuff. All right, that's it.